The topic for Lesson 6.4 is parallel lines and proportional parts. You'll learn how to use proportional parts of triangles and divide a segment into parts. The topic for Lesson 6.4 is parallel lines and proportional parts. You'll learn to use proportional parts of triangles. How do city planners use geometry? Street maps frequently have parallel and perpendicular lines. In Chicago, because of Lake Michigan, Lakeshore Drive runs at an angle between Oak Street and Ontario Street. City planners need to take this angle into account when determining dimensions of available land along Lakeshore Drive. Non-parallel transversals that intersect parallel lines can be extended to form similar triangles. So the sides of the triangles are also proportional. That's proved in Theorem 6.4, the triangle proportionality theorem. If a line is parallel to one side of a triangle and intersects the other two sides in two distinct points, then it separates the sides of the segments of proportional lengths. So in this example, they marked that BD was parallel to AE, and they said that the sides would then be proportional. So this segment, BA, is to CB as the segment down here that lines up with it, DE, is to CD. The way I look at it is right there's my fraction bar. So they did theirs upside down, but it still works. In triangle RST, RT is parallel to VU, which they marked, and the length of SV is 3, the length of RV is 8, the length of UT is 12, and they ask us to find SU, and they were nice and labeled that X for us. Okay, I am going to do something really weird here. I would like to turn our diagram so it looks more vertical. So just imagine you just rotated your book, because then I have it in the same orientation as they had it in Theorem 6.4. So now it's easier to see that SV is to RV as SU is to UT. And I like this orientation better for our first one, so we can see how we set up our proportion. So I'm just going to write 3 is to 8 as X is to 12. And I'm kind of imagining that as my fraction bar. Now it's easy to solve. We can just do cross products. So 36 equals 8x. Divide both sides by 8. And we get x is 4.5, 4.5, 9 halves, however you want to leave it is fine. In example 2, they said in triangle DEF, the length of DH is 18, the length of HE is 36, and DG is half of GF. So they didn't tell us what GF was, but whatever it is, it's twice whatever this guy is. So if we looked at the proportions, the proportion of DG to GF, even though I don't know the lengths, I know that the proportion is going to be, I cancel out my x's, anything divided by itself is 1. So the proportion of the sides is 1 to 2. And looking at DH to HE, the proportions are 18 to 36, which reduces to 1 to 2. So they are parallel because that's our notation for parallel, the two vertical lines next to each other, because the sides are proportional. The reason we can do that is Theorem 6.5, the converse of the triangle proportionality theorem. If a line intersects two sides of a triangle and separates the sides into corresponding segments of proportional lengths, then the line is parallel to the third side. So in this example, if we know that BA is to CB as DE is to CD, then we can conclude that BD is parallel to AE. A midsegment of a triangle is a segment whose endpoints are the midpoints of two sides of the triangle. Sounds kind of similar to midpoint. Theorem 6.6 is the triangle midsegment theorem. A midsegment of a triangle is parallel to one side of the triangle, and its length is 1/2 the length of that side. So in this example, they said if B and D are midpoints of segment AC and EC, so they marked that with the tick marks, so these two are the same and these two are the same. And BD is parallel, they didn't mark that, we'll mark it with arrows, to AE, and then BD must be 1/2 of the length of AE. So if I let this be 2x, this would be x for any number we put in for x. For example 3, triangle ABC has vertices at -2, 2, 2, 4, and 4, -4. DE is a midsegment of triangle ABC. Find the coordinates of points D and E. It was helpful to plot the points first and see where D and E are going to lie. So I know that the parallel lines should be DE and BC. I'm looking at the graph. So I need to find the midpoint of AB and the midpoint of AC. Let's do point D first, so that's going to be the midpoint of AB. So recalling our midpoint formula, we're going to take the x coordinates of our 2 points, which are -2, I'm adding, and 2, add them together and divide by 2, and then take the y coordinates of our points, 2 and 4, add them together and divide by 2. So point D is going to be found at -2 plus 2 is 0, divided by 2 is 0, which is no surprise from the graph. 2 plus 4 is 6, divided by 2 is 3. And now for E, same thing. So the x parts of our points, -2 and 4, add them together, divide by 2. And then the y parts of our points, 2 and -4, add them together, divide by 2. So -2 plus 4 is 2, divided by 2 is 1. And 2 plus -4 is -2, divided by 2 is -1. Next, they ask us to take the same coordinates and verify that segment BC is parallel to DE. Well, remember that parallel lines have the same slope, and slope is change in y over change in x. So for BC, our change in y, we could do 4 minus -4 over 2 minus 4. So 8 divided by -2 would be -4. For DE, the slope is going to be, again, change in y. So -1 minus 3 over change in x. We started with the -1, so we need to start with 1 minus 0. That's not too bad. -1 minus 3 is -4 over 1 minus 0 is 1. So that also has a slope of -4. So that confirms same slopes, they are parallel. Trying to make a little therefore sign. To verify that DE is half the length of BC, we're going to have to use the distance formula twice to find both of their lengths. Let's do BC first, since that's the one they gave us the points for. So BC, our x's, doesn't matter which one we do first. Let's go 2 minus 4, and our y's, 4 minus negative 4. I am lazy, I'm just going to put a plus. And then we have to take the square root of that whole thing. 2 minus 4 is negative 2, squared is 4. And 4 plus 4 is 8, squared is 64. So when we take the square root of that, we get the square root of 68, which simplifies to, move it up so I have room, that could be 2 square root of 17. If you remember that, 68 could be rewritten as square root of 4 times square root of 17, or if you used a calculator, that'll just do it for us. Okay, that was BC. Now we need to do DE. Same thing. Okay, so we're going to do difference in the x's. That's nice. 0 minus 1, or let's do 1 minus 0. And difference in the y's, negative 1 minus 3. Square them, and we have to take the square root of the whole business. So we have 1 squared plus 4, negative 4, but we don't care because we're squaring it. And we get, oh, don't forget my radical sign. 1 squared is 1, plus 4 squared is 16, so I'm going to get the square root of 17, which is definitely half of 2 squared root of 17, so that is a yes. They are in the right proportion. Square root of 17 is half of 2 square root of 17. Okay, so we have corollaries, which recall are special cases of our theorems and can be easily proved from them. Corollary 6.1 says if 3 or more parallel lines intersect 2 transversals, then they cut off the transversals proportionally. So instead of just one proportion, we end up with 2. They're all proportional. And theorem 6.2, if 3 or more parallel lines are cut off, this is the converse, congruent segments on one transversal, then they cut off congruent segments on every transversal. In the figure, Larch, Maple, and Nuthatch streets are all parallel. The figure shows the distances in city blocks that the streets are apart. They ask us to find x. So for getting the parallel lines, you can see there's a nice triangle. There's our triangle proportionality theorem that we can use. So we can go 13 is to 26 as 16 is to x. Do our cross products. And we have 13x equals, I'm going to be lazy here for a second and just leave it 16 times 26 because I noticed something I can use my mental math on, which is always good. The 13 and the 26 will cancel out. So I have x equals 16 times 2 is 32. Yes, you could use a calculator, but it's good to use your brain sometimes. Oh, this looks familiar. A little good old algebra. Find x and y. Well, they marked on the diagram for us that these two segments are equal. So x requires really no geometry at all. We're just doing algebra. So 2x plus 2 equals 3x minus 4. Could subtract. I'm going to subtract 2x from both sides because I know that 3 minus 2 is 1. And then all I have to do is add 4 to both sides. And I've got x. Okay, now we need to rely a little bit on our geometry know-how. If these two segments are the same, then because they're cut by transversals cutting parallel lines, then these two segments are also going to be the same as each other. So now we have another little algebra problem to solve. So 8/3 y plus 7 is in fact equal to 5y. What is this thirds they're doing to us? Okay, well we could get a common denominator. If we took the 5 times 3 over 3, that'd be 15/3. That's better. So now I could subtract 8/3 y from both sides of the equation. And I have 7 equals 15 minus 8 is usually 7. Another 7. How convenient. So now if I multiply by the reciprocal, nice little algebra review, I get my fractions to cancel out. So I have y equals, the 7's also cancel out. So all of that fraction business was for nothing because y equals 3. Okay, summing up parallel lines and proportional parts, a segment that intersects two sides of a triangle and is parallel to the third side divides the two intersected sides in proportion. And if two lines divide two segments in proportion, the lines are parallel.